All right, our next presenter this afternoon is Elliot Schweitzer, who joins us from Pitzer College. Elliot's been working this summer with Nondh, and today we'll hear about their project together, satellite exchange and fire simulations of Milky Way M31 analog systems.
Thank you for the introduction, Gwen. So I want to start us off by introducing you to the types of systems that I've been working with this summer. So we live in the Milky Way, and right next to the Milky Way is another galaxy of similar mass, Andromeda, or M31. So the systems that I'm looking at are simulated systems that are similar to our own, so containing two Milky Way mass galaxies. Galaxies are composed of both the dark matter halos and the stars, although dark matter halos don't necessarily have to contain stars. And here's one of the systems that I'm looking at. This is Romeo-Juliet, and both of these distributions are at the present day. So I also want to clarify some terms that I'm going to be using. First, when I say host or host halo, I'm referring to one of the two Milky Way mass halos in the system. And then every other dark matter halo will be a non-host halo, although I'll often just say halo, which can be further divided into satellites, which are inside one of the hosts, or field halos, which are outside of both of the hosts. So when we look at the local group in the vicinity of the Milky Way and Andromeda, we notice some dwarf galaxies with some peculiar properties. For example, this dwarf galaxy, presented by Yang et al. In 2022, has some mass that looks like it's trailing behind, which is best explained by an interaction with a massive host. However, this dwarf galaxy is not near the Milky Way or Andromeda, which leads to the question, can dwarf galaxies interact with a host and then end up very far away from that host? As it turns out, the answer is yes. What we call backsplash halos are halos that used to be within the virial radius of a host, but are currently outside of the host. And my mentor found that in simulations of isolated Milky Way mass galaxies, backsplash halos are very common. And when we look at the distance distribution of backsplash halos, we see, so this is distance on the x-axis and the fraction of backsplash halos on the y-axis. And these are all backsplash halos of one host and their distance from that host. The blue line here is the distance between Milky Way and Andromeda, and the blue band represents the virial radius of Andromeda. So we see that a lot of these backsplash halos, a large fraction of them, are in the correct distance range to actually be within a second host at the present day. And this motivates the question, the main focus of my research, which is, in systems with two hosts, are halos exchanged between the hosts? So to investigate this question, we need to use simulations, because to determine whether halo is exchanged, we need to be able to track its entire history. So I'm doing this using simulations from the FIRE collaboration, or feedback in realistic environments, which are hydrodynamic simulations containing both baryonic and dark matter physics. These are the same simulations that my mentor uses. And more specifically, I'm using the ELVIS suite, or Exploring the Local Volume, in simulations, which is a set of 3 simulations, each of which contains 2 Milky Way mass hosts. So here are the 3 simulations that I'm looking at. Romeo-Juliet, as I showed you earlier, Romulus-Remus, and Thelma-Louise. These are their dark matter distributions at the present day. And another thing to consider about simulations is that we have a resolution limit. So the smallest dark matter halos that we're able to resolve with these simulations are about 10 to the 6 solar masses. I also want to introduce some terms that are specific to my project. So because we're looking at both the present day location and the histories of those halos, there are a lot of ways to categorize them. And just a heads up, I will be using these terms for the rest of my presentation. So true field halos are halos that have never been inside a host. True satellite halos were either formed within a host or entered a host and never left. And the rest of the halos will be backsplash halos, which used to be inside a host and are currently outside that host, which these can be separated into one-host backsplash halos, represented by the yellow curve, which have only interacted with one host, exchange satellites, which used to be inside of one host and are currently inside the other host, and two-host backsplash halos, which are backsplash halos of both hosts. And the most important categories for my project are exchange satellites and two-host backsplash halos, since these are the exchanged halos that have interacted with both hosts. So, like my mentor, I find that backsplash halos are very common. Out of all of the field halos that we looked at, we see that about 32% of them are backsplash halos, with some variation between the simulations. And we also find that halo exchange occurs in all three simulations, with about 1.8% of all of the satellite halos being exchanged, so originating from the other host. There were only 3 two-host backsplash halos across all the simulations, which is why I didn't include them in this table. So they happen, but they're very rare. We also see that there's significant variation between the amount of exchange that happens in the different simulations. In particular, you see that Thelma Louise has hardly any exchange satellites. One reason for this could be that Thelma and Louise were farther apart for the majority of their evolutionary history as compared to Romeo and Juliet and Romulus Remus. And then for reference, the Milky Way currently contains about 66 known satellites. So with these predictions, we might expect that one or even more of the satellite galaxies in the Milky Way could actually have originated from Andromeda. So now I want to show you a movie of all of the backsplash halos in Romeo and Juliet, just so you can get a sense for how these systems evolve. So one thing to note about this is that the vast majority of exchange satellites actually end up in the second host, which is the less massive host. And this is a trend we see across all of the simulations, where the majority of exchange satellites come from the larger host to the less massive host. And I'm going to play this video one more time, and I want you to focus on the region between the two hosts. So one other thing that we see about these systems is that a lot of the single host backsplash halos that are currently in between the two hosts are actually moving towards one of the hosts, which implies that a lot of these single host backsplash halos will actually become exchange satellites in the future. Now I want to look at some properties of these halos. So first I want to show you the mass for all the different categories. We're looking at the peak mass here because we expect that the more a halo interacts with a host, the less massive it will be. So the peak mass should represent the pre-infall mass. And we see here that we're drawing from a very similar distribution of initial halos before they interact with the hosts. With the exception that the two-host backsplash halos look a little bit more massive than the rest, but there are only 3 of these, so these are very low number statistics that we're working with. So then when we look at the present day masses, we see exactly what we expect. So we see that the true field halos are the most massive. The one-host backsplash halos are slightly less massive than the true field halos. And the two-host backsplash halos have lost a lot of their mass, some of them up to one of them up to 90% of its mass. And the reason for this is tidal stripping, where a halo interacts with a more massive host and has mass pulled away from it by the larger gravitational potential well. Now, when we look at these satellites, we see the opposite trend, where the true satellites are actually less massive than the exchange satellites. But this also makes sense with what we know about these systems, because true satellites have spent the vast majority of their histories inside of a host halo, whereas the exchange satellites have spent a long time outside of both hosts, so they haven't had as much time to be tidally stripped. Now I want to show you the radial velocities. And this is just for the satellites, because this is more focused on what we might want to observe to look for satellites in our own Milky Way, exchange satellites in our own Milky Way. So when we see these radial velocities, we actually see that the distributions between true satellites and exchange satellites are remarkably distinct. True satellites are generally clustered around 0, which means they're not moving towards or away from the host. Whereas exchange satellites heavily favor either moving towards the host, which is the negative velocities, or away from the host, which is the positive velocities. So the reason for this will be because the exchange satellites have highly elliptical orbits. So they're going to be because they're coming from the other host, they have to be traveling almost directly towards the second host in order to make it inside the second host at the present day. So that will also mean that when they go near the host, they're going to have very elliptical orbits. So they're going to spend most of their time going away from or towards the host. Whereas true satellites are more likely to have less elliptical orbits and also spend most of their time just traveling perpendicular to the center of the host. So in conclusion, we see that halo exchange occurs in all three simulations with about 2% of all the satellite halos, or 2% all of the satellite halos being exchanged. We also see that, as we expect, the mass loss experienced by a halo corresponds with how much it's interacted with a host. We see that exchange satellites tend to have highly radial orbits as compared to true satellites, and also that many halos look like they will become exchange satellites in the future. As for next steps, we want to look into other properties such as metallicities, velocity dispersions, stellar content and distribution, and star formation histories, because these are more observable properties that we could compare to satellites in the Milky Way. And also investigate how host properties such as mass difference and distance can affect halo exchange. Thank you.
So I think you said in all three of the simulated systems, the exchange satellites tended to come from, or preferentially come from the more massive host to the lower mass one.
Yes.
That might not be what I expected. Do you have like good intuition for why that's the case?
Yeah, I talked about it with my mentor, and we think that a likely reason for this is because the more massive host will just start with more satellite halos. So there will be more backslash halos from the more massive host, and less backslash halos coming from the less massive host.
Other questions?
What were the virial radii you were working with for your simulation?
Yeah, you mean like what are VO radii or what were them?
What the distance was?
Yeah, they were ranging from about 300 to 350 kiloparsecs.
Gotcha. If you kept increasing the size, would you expect more satellite exchange?
Yes, because well, okay. The viewer radius is not something that we are controlling. It's defined based on the density within the viewer radius. So that is not a free parameter. But if the viewer radius were larger, then it would just capture more halos. So we would expect a little bit more halo exchange.
Any signature still left in the 2D velocity vector of the exchange satellites? Am I thinking specifically with respect to the other galaxy?
We have not looked at the 3D velocity vectors, but that's definitely something we could look into.
Interesting, because
Yeah.
there are 60 or so satellites known in the Milky Way, so maybe one of them is from LMC.
Hopefully, that'd be really cool.